Okay, on 72, we're saying let a of x equal the integral from 0 to x of f of x dx. Remember, that's that area function that we're looking at, where f of x is the function shown below. So what are we looking at? We are looking at a prime of x, all right? So we can immediately determine the local min and max and points of inflection of the original function a of x, as well as where it's increasing, decreasing, concave up or concave down. And then also the absolute max of a of x. Sure, we can do all of that. So we're going to look at this on the interval from 0 to e. And we're going to think about, of course, first where a prime of x is equal to 0, because that's going to be possible critical numbers. So we have that at b and then at d. All right, now notice from a to b, or from 0 to b, the function is positive, and then from b to d, it's negative, and then it's negative again at e. So all we have here is an increasing, decreasing. We have a max at b, and our function is increasing, decreasing, and this is probably, it's probably flat at d, the actual graph, and then this one is a max if we were to look at a of x. Okay, so we can say now that it's increasing on the interval from 0 to b, it's decreasing on the interval from b to e. Okay, let's talk about, and then we have a max at a local max at b. Now the other place that we would need to check to see is the endpoints, whether we have an endpoint value that is a max, either 0, b, or e. So to check for absolute maxes, you need to look at the endpoints. So we want to figure out what a of 0 is, a of b, and then also a of e. Now remember, a is the cumulative area function. So at 0, you haven't gotten any area yet, so it's just 0. Now at b, we've got all of this area. We don't know what it is, but we know it's positive. And what we want to do is compare the cumulative area at b to the cumulative area at e and see which one's bigger, because that one's going to be the absolute max. Now what you should notice is that as you move to e on the interval, all of the area is underneath the x-axis. So that's negative area. So the function value big A at b is going to be more than big A at e, because the area that you accumulate when you move from b to e is negative, so it's going to cancel out some of this. So that then tells us, we don't know whether a of e is positive or negative. It's probably still positive because it's not as much area right here, but we do know that it's less than a of b, which is why this then will be your absolute max at a of b. Now to determine concavity, you're going to want to look at the mins and maxes of the derivative, which is the graph that you're looking at right here. And so the function, the derivative is changing. Notice the derivative is changing from increasing, and then it becomes to, and then it starts to decrease. So if your derivative changes from increasing to decreasing, then your second derivative must change from positive to negative, meaning that your original function is concave up and then concave down, and you have a point of inflection at a. And then the same thing is happening at c. At c, you're going to have a point of inflection, but you're going to go from decreasing to increasing. So this is going to be concave down and then concave up. And then finally, notice at d, at that point where it's flat, you go from increasing to decreasing again. So you do have another point of inflection, and you're concave up and then concave down. Okay?